So in this video, we're going to learn about a very important method or a technique. It's called regression analysis. So regression analysis is very simple. It's simply a data analysis technique. What it can do is it helps to predict the trend in the data. So this is something that you have to learn if you are a chemical engineer. So this is absolutely essential for to solve a lot of chemical engineering problems. So we need this method to solve a lot of engineering grade problems because you're going to encounter a lot of data that explain a particular system, or it can be even a simple experiment that contains some set of data and you have to predict what's happening in that particular system. So for that you need some method. So for that regression analysis become really useful. It also has wide applications in other areas of science. So I can give some examples like when we need to use this in chemical engineering. I mean when we need regression analysis to solve some chemical engineering problems. So for example, in chemical engineering, the most common examples they come from the reaction engineering. For example, you may have some chemical reaction that's happening here and you have some time and you want to see how the product formation changes with respect to time during the course of chemical reaction, something like that. And then just imagine you also have some analytical method that also allows you to measure how your reactant concentration change with respect to time during the course of the reaction. Or sometimes you may encounter problems that contains data like time versus productivity or maybe even percentage conversion. This is a very common problem in chemical engineering. So we have some chemical reactor where we perform some reaction in batch mode, and all we are interested is how the percentage conversion changes with respect to time. So you may have some data, so you need to predict how your percentage conversion changes with respect to time. So how you do that? Obviously you have to develop some mathematical function. So what that mathematical function looks like? So just for example, you have time, and let's say this is your percentage conversion on the y-axis, and you have time on the x-axis, and you have some data. So what this graph means is your percentage conversion is changing continuously with respect to time, and eventually it reaches some plateau. So eventually it comes to some plateau. So that's the trend that we can observe from such a data. And all we need to find is, so you need to find an equation that can predict the change in data which is happening with respect to time. So typically the time which is plotted on the x-axis, this is something we call it as independent variable, and then anything that we plot it on the y-axis, that is in this case you have percentage conversion, that's called a dependent variable. So this depends on the independent variable, in this case time. So which means a dependent variable is something that's going to change with respect to our independent variable which is plotted on the x-axis of the graph. So what is our intention now is to predict some equation, some function, let it call f of x, or in this case f of time. So this function, so this is the function of this expression. Whenever I say function, this is a mathematical expression. So that mathematical expression is a function of your independent variable, which in this case is time. So you may need to find some expression or this particular mathematical function so that can predict your dependent variable, how your dependent variable changes with respect to the independent variable, which in this case is time. Yeah, so we plot some other example. So you have something, let's call this x. So x is plotted on the x-axis, y is plotted on the y-axis in this graph. So x is your independent variable, and then y is your dependent variable. Yeah, and let's say we have some data that looks like that. So this is a very simple data. So when you see this data, you can see something is changing with respect to time. sorry, I mean the y is changing with respect to x, and it follows a linear trend. So if you draw a trend line, that will look something like a straight line, and if you take this slope, that slope will be equal to m, which will be dy by dx, and then you may have some intercept. Let's call this intercept as c. So this change in trend, so the change in y with respect to x, can be predicted using a function which is a function of x. So this will look like mx plus c. So y is equal to something, a function of x. So y is your dependent variable, x is your independent variable. So we are developing some mathematical equations so that allows you to predict y as a function of x. So that should look like mx plus c. So this is the function that can predict how y changes with respect to x. What the regression analysis, so where this word regression analysis comes from. So regression analysis is something, if you want, you can call it as a data analysis technique, or you can call it as a method to test whether the function which can predict how your dependent variable changes with respect to independent variable. So it checks the accuracy of the mathematical function. So it provides a way to test the accuracy the function f of x that predicts the change in dependent variable with respect to the independent variable x. So how we do that? So what it predicts is it predicts the error distribution. So regression analysis is a method where we predict the error distribution between the experimental data, sometimes we call it as observed data, and the ones predicted using a mathematical function. Mathematical function, or it can be or you can call it as mathematical expression. So what do I mean by this? So let's say we have an example problem, so where we need to predict how concentration changes with respect to time. So let's say we have time is our independent variable, and then concentration, which is our dependent variable. So it can be in units. Let's put gram per liter. Time, let's say, call it in minutes. So you have 0, 1, 2, 3, 4, 5, 6. And then you have some concentration that starts from 100. Let's say 90, let's say 85, 80, let's say 75, 70, and let's say 65. So we have something on the x-axis 0, 1, 2, 3, 4, 5, 6, and then you have some concentration 100, 95, 80, 75, 70, 65. So what's our job is we have to find a mathematical function. So mathematical function that can predict the concentration. So concentration should be a function of x. In this case, concentration should be a function of time. So how to do that? So let's say we have some function, and this function successfully predicted the concentration. So what we have, concentration, and for the sake of convenience, what I'm going to do is I'm going to label all the x's. So I'm going to do something like that: x1, x2, x3, x4, x5, x6, and x7. And similarly, I'm going to label the concentration as y1, y2, y3, y4, y5, y6, y7. So this is for the sake of convenience. So if you have n number of data points, you will get xn minus 1, and then next will be xn. If we have similarly for the dependent variable, it will be yn minus 1, and then the last value will be y suffix n. So that's how we are going to label it. So this function, let's say we have some function that predicted this equation. So let's call the predicted ones. Let's say this function predicted the y value for the given x1, and the predicted value, let's call it as maybe let's call it as y1 comma p. P stands for predicted, y2 comma P, y3 comma P, and then so on, y7 comma P. So if we have n number of data, so this will be y will be equal, we can write the y as y n minus 1. The last point data point will be y suffix n. So how we label here, so we have a x1, or we can call it x suffix I. So that's um, our, our independent variable, and then we have y suffix I, that's our dependent variable. Okay, let's label yn minus 1 comma p, yn comma p, and then we have something called as the predicted ones, yi comma p. So what we have to find now is the error. So the error distribution, what do I mean by that? So the error distribution is something like, so you have some experimental, so follow the blue line. So you have some experimentally obtained value, or we can call it as an observed value, and this is something which is predicted using a mathematical function for x1. So we predicted y1, what the expected value, if you are, I mean, what could be the expected y1 value if for the given x1, which is your independent variable. Yeah, so let's do that. So what do I mean by that? So we are trying to predict what could be the concentration when time is equal to 0 minutes. So actually that should be equal to initial concentration, but still your mathematical function should predict that one successfully. So how to test whether this function c is equal to f of x successfully predicted the concentration for the given inputs, which in this case is time. So how to test that? We have to calculate something called as error. So what we do this is, error is very simple. So let me write this, how to write an error. So what is this error? How do you get this error function or error distribution in the data? So error is just your yi minus yi predicted to the whole square. So this is your actual experimental data. This is something that we predicted for the given xi. Xi is your independent variable, and then you take the difference that should give the something plus or minus with respect to your experimental data yi, and then you take the whole square. What do I mean by this? So this is error, and then you take the whole square. So what this function error is equal to yi minus yi predicted raised to the power 2. It's nothing but sum of the errors squared. So what we're trying to do is, we're trying to minimize the error distribution between the experimental data and the predicted value using a particular function, which is error function called sum of the error squared. And this method, that's why this is called the method of least squares. So our topic is regression analysis, but what we are learning at the moment is we are performing the regression analysis using the method of least squares. So that's the topic. There are other methods. Some is the normal graphical method. You plot time versus concentration, and then you draw a trend line, and then you estimate the equation for that particular trend line. So that's a graphical method, which has its a lot of disadvantages, because how you draw the line, that depends on the user. Yeah, so it's not a universal, it's not going to give some global values. Yeah. And another one is something called as the method of moments. So this is something I can cover in a separate video. This is also very useful method of moments, and there are other method called the method of group averages. So I can cover these topics in a separate video, but for the moment we are performing regression analysis using one of the most widely used method. Almost every research lab, every scientist, every guy in chemical engineering is going to use this method of least square is commonly used method. So that's what we are learning at the moment. So the method of least square, what it means is, this value, the error function, the sum of the error squared should be as small as possible. So that's why the name method of least square. And this method was actually, or this terminology, method of least square, was coined by French mathematician Adrien Mary. I don't know how to pronounce. I believe it's Legendre. This is something you might have learned in general mathematics, Legendre's polynomials. So this term was coined in the year 1806. So that's the method of least squares. So let's try to solve few functions using the method of least squares. So let's begin with something called a polynomial function of order 2. So what do I mean by that? So you have some data, as I said before, say like you have some data, say x1, x2, x3, x4, and say x5. So this is your independent variable, and you have some dependent variable y1, y2, y3, y4, and y5. So this is your dependent variable, and let's say we have some function that predicted the values of y for the given values of x, and that function looks like, so let's say that function f of x is something like a plus bx of I, x suffix I plus cxi the whole square. So what this equation mean? So if you know the a value, if you know the b value, if you know the c value, where a comma b and c are constants, if these numbers are accurate, then this function can accurately predict the y value for the given x value. So if you want to predict y1, then y1 should be equal to a plus bx1 plus cx1 square. Similarly, y2 should be equal to a plus b sub x2 plus c x2 whole square. Similarly, y5 should be equal to a plus b x suffix 5 plus c x suffix 5 whole square. If we have n number of datas, it will be equal to y suffix n should be equal to a plus b x suffix n plus c x suffix n raised to the power 2. And then what we need to do, so let's call this predicted values y1 comma p, y2 comma p, y5 comma p, and similarly yn comma p. So now we have to calculate the error distribution between the predicted value and the experimental value. So this will be obviously equal to yi minus yi predicted raised to the power 2. So this is something we can predict provided we have the value a comma b comma c. So how to get this value? So we know that for any given values of xi, to predict yi successfully, the error distribution, the error function should be minimum. So this is the key message. So if you understand this, then we can solve this problem. So let's solve this problem. So for e to be minimum, so let's call error using notation e. So for e to be minimum, change in error with respect to change in a, and the change in error with respect to change in b, and the change in error with respect to change in c, this should be equal to 0. So what do we mean by that? So it is something like either you can go for a trial and error method. So you randomly substitute some values a, b, and c until you observe error is at minimum. But this is something we don't have to do. Instead of going for trial and error method, we know this rule. If e should be minimum, then whatever the change which is happening, change in the error with respect to a, that should be equal to minimum, and likewise the other constants, change in error with respect to b, change in error with respect to c, it should be equal to 0. So what happens means, if your a value is correct, then whatever the change in error, or what, that should be equal to 0. And then likewise, so how to explain this? So you have, say like a is equal to a1, a is equal to a2, a is equal to a3. So you keep on changing some values. So but at some point you will notice that error function will be almost equal to 0 or absolute 0. Yeah? So that's the correct value for your, so let's say when a is equal to a1, then the error, the change in error should be minimum. So what do I mean by that? So let's try to plot something like so let's plot it something like this. This will make it a bit more easy. So let's say we are plotting e on the x-axis, and then the a value on the no, maybe we can plot a on the x-axis, and let's say we plot e value on the y-axis. So let's say we have a Say a is equal to a1 and you have some error function here, the error value here, and then for a2 error is something like this, a3 error is something like this, a4 error is something like this, and then a5 error value is something like this, and a6 your error is something like this. So when I try to plot this, you may get some trend like this. So what is this one? So we can call this trend line as change in error and then change in with respect to change in a values. Yeah. So this will be equal to, so when the error is minimum, so that point will be equal to this particular function being equal to 0. So it's a change in error with respect to change in a, that should be equal to 0. So what do I mean by that? So if you follow this line, so something is changing, something is changing, something is changing, something is changing, and at the minimum something is stationary, which is constant, and anything which you differentiate a constant with respect to the independent variable, that will be equal to 0, and then again it starts to change. You know? So how do you find the a value when your error is minimum? So that's something you can find by taking the partial derivative of that error function with respect to your constant, in this case a. You know? So this should be equal to 0. So that's the condition when the error will be equal to minimum. The same rule applies for how how the error changes with respect to the constant b. Something changes and then you predict the particular b value where your error will be minimum. So that point should be equal to change in error with respect to change in b, that should be equal to 0. So this represents the stationary point in this line where your error will be minimum. And similarly, you should also find something with respect to c. So the change in error with respect to c, that should be equal to 0. So this should be, so when change in error with respect to c, if it's equal to 0, so that represents the point where your error will be minimum. Also remember that so you may have a, let's plot it here. So let's say you have error, you have some a value, you may get something like this in this function. So this is a stationary point, this is a stationary point, this is a stationary point. So let's call, so this one is, let's call this is like a global minimum where your error will be minimum, and this is something like a maximum. So we have to make sure our change in error with respect to the constant, to make sure this is a minimum. So we have to develop a function between e versus a. Let's say a function which is a function of e, and if we take the partial derivative of d squared e with respect to dA squared, that value should be positive. So what does that mean? It means if this value is positive, then e is minimum. This is something that we can prove. Obviously we are now deviating from the topic, but just to make sure that we have some error, we have some constants a comma b comma c. Let's say we have some functions, and so this is the point that we are targeting. This point, some stationary point where your error will be minimum. So this, so change in e with respect to a, or change in with respect to b, or with respect to change in c, that should be equal to 0. So that represents the point where your error is at minimum. And if you want, we can even calculate d squared e by dA squared, d squared e by dB squared, and d squared e by dC squared. And then if we calculate the corresponding a comma b and c, and if we manage to get some value which is positive, then that means e is minimum. So whatever I said, we are just going out of the topic. So let's continue with the method of least square. So let's go into the topic. So we are trying to fit a data xi comma yi using a polynomial function that something looks like a, so yi predicted, that's equal to yi predicted, that's equal to a plus bx of I plus cx of I the whole square. So the method of least square requires error should be minimum. Error should be minimum, if not 0. So then, which means we have to meet the following conditions. The change in error that should with respect to A should be equal to 0. The change in error with respect to B should be equal to 0, and the change in error with respect to C should be equal to 0 for E to be minimum. So let's try to solve this equation. So we have yi predicted, that's equal to A plus bxi plus cxi square, and then we can define something called as error. So error is equal to, let's say, e1 square plus e2 square plus e3 square plus e4 square plus e5 square. So we have 5 different x values and we have to predict the y value, and we are trying to get the error between the experimental data and the predicted data. So what is e1? So that's y1 square minus y1 predicted, y1 minus y1 predicted to the whole square plus y2 minus y2 predicted the whole square plus y3 minus y3 predicted whole square plus until y5 minus y5 predicted the whole square. We know that for E to be minimum, so dE by dA comma dE partial derivative of E with respect to B, partial derivative of E with respect to C, that should be equal to 0. So that's the condition where your E will be minimum, but this is something we can calculate. So let's plug all the values here. So we have y1 minus, so what is your y1 predicted? So that's nothing but minus a plus bx1 plus cx1 the whole square plus, expand this equation, y2 minus a plus bx2 plus cx2 the whole square plus, we can write up to y5 minus a plus bx5 plus cx5 the whole square. So now we have to take the partial derivative of this equation. So how to do that? So we have, let's begin with how the error distribution, how the error changes with respect to change in A value. So let's calculate dou E by dou A. This should be equal to 0, as I said before. So let's try to differentiate each of these terms in this expression. So the first one should be equal to, I forgot to put the whole square, whole square, whole square. Yep, because this is something y experimental value minus y predicted value raised to the power whole square. So that's how we define the error function. And the method of least square is we are trying to minimize the sum of the error square to minimum value. So whatever the errors raised to the power 2, that should be at minimum. Yep. So that's the principles of least square. That's the definition for the principles of least square. So let's do this mathematically. So let's try to calculate how the partial derivative of E changes with respect to A. So this is one of, and this should be equal to 0. So let's try to calculate. So we know that error is given by summation of y of I minus y of I predicted. So this is equal to summation of y of I minus A plus bx of I plus c x of I the whole square. And then, sorry, this raised to the power square, and then here again square. So error is actually your y experiment minus y predictor raised to the power whole square. So this is the errors square, but since we are going to sum for different experiments, so this is be equal to the sum of the error square. If you want, you can even calculate this or define this error function as sum of the errors squared. So let's see how to do that. So this is how we define error. So we need to differentiate this error function, partial differentiate with respect to A. How to do that? So let's try to do this. Differentiate, you have 2, so 2 comes in the front, multiplied by y of I minus A plus bx of I plus cxi whole square. And since we are differentiating with respect to A, So it will be 1, and since you have a negative sign here in the front, so it will be minus 1. Now, so if you expand this equation, it should be minus 2 y of I minus a plus bxi plus cxi whole square, and this should be equal to 0. So this is the condition. So when partial derivative of e with respect to a equal to 0, so that's one of the condition for the error to be minimum. So you can divide both sides by minus 2, so that makes this equation minus 1 into y of I minus a plus bx of I plus cx of I the whole square, cxi squared, sorry, and that's equal to 0. Or simply you can write it like y of I is equal to, so I forgot to add the summation sign, so summation here, summation here, summation here, and then summation of yi is equal to summation of a plus bx of I plus cxi the whole square. Yep. So what's this mean? So let's say we have I is equal to 3. So what do I mean by that? So we have 3 experiments, which mean we will have 3x, x1, x2, x3, and then the corresponding experimentally obtained y value will be y1, y2, y3, and let's say we also predicted that one. So y1 predicted using the expression a plus b x plus cx square, y2 predicted, y3 predicted. So how we do that? If we know the constants a, b, and c, then we can predict a plus bx1 square, sorry, bx1 plus cx1 square. Similarly, for y2 predicted will be a plus bx2 plus cx2 square. y3 predicted will be a plus bx2 plus bx3 plus cx3 square. So if you want to calculate dou E by dou A, how to do that? So this is something we already know. So dou E by dou A is given by here, this equation, which is in this box. So which is nothing but, so dou E by dou A. So how do we get that one? So that will be, so y1 minus a plus bx1 plus cx1, and then y2 minus a plus bx2 plus cx2, y3 is equal to y3 minus bx3 plus cx3. So this is the partial derivative of e with respect to a according to this expression. Yep. So if we take a sum of this equation, so how will you write? So if we take a sum, so that will be, so we have x1, we have y1, so we know how to get the y1 predicted, and likewise we have x2, y2, and then y2 predicted, and we have x3, y3, and then corresponding y3 predicted. So from there we can get the error function, or the change in error with respect to a. So let me write that equation. So let me write, so I said we have I is equal to 3, so which means we have x1, x2, x3, y1, y2, y3, and then the y1 predicted, so which is given by a plus bx1 plus cx1 square, a plus bx2 plus cx2 square, and a plus bx3 plus cx3 the whole square. So dou E by dou A, how it will be? So this will be equal to, basically equal to 0. So I already showed you how to do the partial differentiation of E with respect to A. So let's write this here. So you will have say something like y1 minus a plus bx1 plus cx1 square raised to the power 2, and then you also have and then we have one more, y2 minus a plus bx2 plus cx2 square plus y3 minus a plus bx3 plus cx3 square. Yep. So if you sum this value, how it will look like? So this will look something like, so if we take y on one side and then every other parameter on the right hand side, so it will be y1 plus y2 plus y3. So that will be equal to, so you have 1a, 2a and 3a. So that will be 3a's plus you have b, something that we can take it in common. So it will be x1 plus x2 plus x3 plus you can take c common, and then it will be x1 square plus x2 square plus x3 square. So you can simply write this equation as summation of y of I, where I range from 1 to 3, that should be equal to, so 3 is nothing but the number of experiments, or we can say call it as I multiplied by a, plus b summation of x of I, where I range from 1 to 3, plus c summation of I equal to 1 to 3 x of I the whole square. Or if you want, you can write it in a general term. So let's say I is equal to n, which means we have n number of experiments. So in that case, it will be summation of y of I, y is equal to 1 to n, equal to n multiplied by a plus b summation of I is equal to 1 to n x of x I, plus c summation of I is equal to 1 to n and xi whole square. So this is, I'm going to box this equation. So this equation is called the normal equation. So let's call this as equation 1. So in this equation you have three unknown three unknown constants a, b and c. If we need to solve three constants, we need at least three equations. So the remaining two equations, which will be called as normal equation, that will be something that we can obtain by taking the partial derivative of a with respect to b, and then the partial derivative of a with respect to c, and set that resulting expressions to 0, and only then the conditions e will be, the condition e will be minimum will be satisfied. Yeah. So if e should be minimum, then the change in the partial derivative of error with respect to a, and the partial derivative of error with respect to b, and the partial derivative of error with respect to c, they all should be equal to 0. So that's the must condition. So let's try continue to derive how the partial derivative of error e with changes with respect to b, and how the partial derivative of e with respect to c changes with respect to c. Calculate dou u by, so dou b, so that should be equal to 0. So how do you do that? So maybe let's write, so what we are going to do is, so you have this function, just follow the red line. So you have y1, and then you have, this is our predicted function. So now we have to differentiate with respect to b. This y1 minus this whole function is nothing but error, so we have to differentiate the error with respect to function b, with respect to the parameter b. So let's do that. So that will be equal to, same again, 2, so y1 minus a1 plus bx1 plus cx2 whole square, x2 raised to the power 2, and now we are differentiating with respect to b, so that should be equal to minus x1. So plus, so now, so plus we do for the next y2, so 2 y2 minus a1, I mean like a, sorry, this is just a plus bx2 plus cx2 whole square, so this should be x1, sorry, x2 whole square multiplied by minus x2 plus 2 y3 minus a plus bx2, sorry, now we are trying for a3, so x3 cx3 whole square minus of x3 plus, we can go for the fifth term, so 2 y5 minus a plus b s suffix 5 plus c x suffix 5 the whole square multiplied by minus of x5. So if you want to write it in general terms, so this will be just dou u by dou b will be equal to 0. This will be equal to 2 y of I minus a So this will be like sum where I is equal to 1 to I. So a plus b is x of I plus c x of I whole square multiplied by minus x of I. So similarly, we can also differentiate the same expression with, if we go back to this equation, follow the red line again. So this is something we can differentiate again with respect to c, to dou e by dou c, and we can set it to 0 so that the error will be minimum. So let's calculate the change in error with respect to c value. So it's again simple. So all you need is to differentiate. So differentiate again 2 multiplied by y1 minus a plus bx1 plus cx1 square. And now we are differentiating with respect to c. So this should be equal to 2 of x, so minus, because you have a minus sign here. So minus 2x plus again 2 y2 minus a plus b x suffix 2 plus c x suffix 2 raised to the power 2 multiplied by minus, this should be minus 2x1, this should be minus 2x2 plus 2 y3 minus a plus bx3 plus cx3 whole square multiplied by minus 2 x suffix 3 plus, we can write the last term, so 2 y5 minus a plus b x suffix 5 plus c x suffix 5 whole square minus 2x suffix 5. So if you want to write it in a general term, so this will be equal to dou u by dou c should be equal to sum of all the terms. I is equal to 1 to I, and it will be equal to 2. So this will be equal to 2 multiplied by y of I minus a plus b x of I plus c xi whole square multiplied by minus 2x of I. So this should be equal to 0. So for the error to be minimum, dou e by dou a and comma dou e by dou b comma dou e partial derivative of error with respect to c, that should be equal to 0. Only then error will be equal to minimum. So we can write, let's write dou e by dou a. So dou e by dou a, this is something calculated. So I will write it again one more time. So this is equal to so if you write it in general terms, so this will be equal to, so dou e by dou a. So the in general we can write it like minus 2 y of I minus a plus b x of I plus c x of I whole square. So this should be equal to 0. So which means y of I minus a plus bx of I plus cx of I whole square. This is a whole sum. Yeah? So I is equal to 1 to I will be equal to, sorry, yi. So this, so change in error with respect to change in a, that should be equal to sum of I is equal to 1 to I yi minus a plus bx of I plus cx of I the whole square. So this should be equal to 0. So we can expand this one. So sum of I is equal to 1 to I y of I, that should be equal to a plus b summation of xi plus c summation of xi square. So let's call this as equation number 1. And similarly, you can write dou e by the change in error, partial derivative of the error with respect to b. So this is something we already calculated. So I wrote the general equation as well. So which is here. Just follow the red arrows which I'm drawing now. So I'm going to rewrite that in the next page. So that should be equal to summation of I is equal to 1 to I 2 y of I minus a plus bx of I plus cx of I raised to the power 2 multiplied by minus x of I. So we can just multiply this term throughout here. So that should be equal to summation of 2x of I, y of I minus, everything is plus here. So minus into minus become plus. So that's plus a plus b into x of I plus c into x of I raised to the power 2. Close the bracket. So this is equal to 0 because dou e change in error with respect to b, that should be equal to 0 for e to be minimum. So this means x of I, so 0 by 2, that becomes 0. So x of I equal to summation of x of I equal to a plus b summation of x of I plus c summation of x of I the whole square. So this, you get some equation that looks like that. So this is your equation 2. Sorry, this should be, so you're multiplying xi. This is not correct. So if you multiply xi with respect to all the terms in this equation, so you get dou e by dou b with respect to b. I is equal to 1 to I, 2 x of I, y of I minus a x of I. So you have minus sign here, so that makes this should be minus, and since you have minus, this becomes plus axi plus bxi whole square plus cxi raised to the power 3. So this is equal to 0. So we can rearrange this equation. So 0 by 2 becomes 0. So which means you can rewrite in something like x of I, y of I. This should be equal to summation of xi plus b summation of xi the whole square plus c summation of xi the whole cube. So xi raised to the power 3. So this is something we can call equation 2. So this equation was obtained from this equation. Change in error with respect to b, partial derivative of error with respect to b is equal to 0. So let's call this as equation number 2. So now we can calculate the change in error. See, so we already calculated how the error changes with respect to A, and then how the error changes with respect to B. So now we can calculate how the error changes with respect to C, and this should be equal to 0. So how to do this? So you have again same 2 y1 minus, so what we are differentiating now is, we go back to this expression. So you have this y1, you have a plus bx1 plus cx1 2, just follow the red box. So we are differentiating with respect to c value. So how to differentiate? So 2y1 minus a plus bx1 plus cx1 square. Now we are differentiating with respect to c, so that means it should be minus, because you have a minus sign here. So minus x1 square plus 2 into y2 minus a plus b x of 2 plus c x of x2 whole square multiplied by minus x2 whole square, plus we can write for the fifth term 2 y5 minus a plus b x of 5 plus c x5 whole raised to the power 2 multiplied by minus x5, sorry, yeah, x5 whole square. So if you want to expand this equation, so what we have here, so we have change in error with respect to 0, with respect to c, so that should be equal to 0 for the condition e to be minimum. Yeah? So let's summarize. We already calculated dou e by dou a, dou e by dou b, change in error with, or the partial derivative of the error with respect to c, that should be equal to 0. All should be equal to 0 for e to be minimum, or in other words, the error to be minimum. So let's rewrite this equation, and then, so let's say dE by dou A. This is something we calculated just now. So let's assume we have I number of values. So x1, x2, until x of I, y1, y2, until y of I. Yeah, so let's write this equation. So I is equal to 1 to I. So minus 2 y of I minus a plus b x of I plus c x of I square, that should be equal to 0. So we can write this equation in a simpler form. So 0 by 2, that becomes 0. So we can expand the other expression. So y of I minus a plus b x of I plus c x of I the whole square. So we can keep yi on the one side. Y of I should be equal to a plus b into summation of x of I plus c into summation of x of I raised to the power 2. So we know this is equal to 0. So that's how we come to this equation. So let's box this equation. And I'm going to call this equation as equation number 1. So let's rewrite dou E by dou B. So what we calculated now. So we go back here. So that's the equation dou E by dou B. Just follow the pen. So we are going to rewrite this expression. So let's write this equation. So what we have here, sum of 2 y of I minus a plus b x of I plus c x of I square multiplied by minus x of I. So if you can multiply xi throughout the equation, so that should make, note that this is the whole equation is equal to 0. So that makes summation of 2 into y of I x of I minus a x of I plus b x of I the whole square. Oh, sorry, so this should be minus because you have minus xi, so this whole term become plus c x of I cube. That's equal to 0. So we can simplify this equation to 0 by 2, that becomes 0. So that makes, so summation of y of I x of I equal to a summation of x of I plus b summation of xi raised to the power 2 plus c summation of xi raised to the power 3. So this, let's box this equation. I'm going to call this equation as equation 2. So this equation 2 comes from by taking the partial derivative of the error with respect to b. So dou E by dou B and setting this equation to the resulting expression to 0, and that's how you get the equation number 2. So now so we have dou E by dou C, just now we calculated here. So I'm going to write this equation in a general format. So how do you write it? So dou E, general format means I'm going to assume I have I number of values, so which means dou E by dou C, partial derivative of the error function with respect to C. So that should be equal to, how do you write, 2 multiplied by y's of I. So let's put summation I is equal to 1 to I, y's of I minus a plus b x of I plus c x of I the whole square multiplied by minus x of I the whole square. So just multiply this whole term with minus x of I square. So what you will get, so summation of 2x minus x of I square y minus, so minus x of I square, and you have minus sign here, that makes it plus a multiplied by, sorry, x of I square plus b x of I cube plus c x of I raised to the power 4. This whole term is equal to 0. So which means you can simplify this equation. So you take this one to the other side. So summation of xi squared multiplied by yi, that should be equal to a summation of x of I raised to the power 2 plus b summation of xi raised to the power 3 plus c summation of x of I raised to the power 4. Let's box this equation. So I'm going to call this equation as equation 3. So we got three expressions or three equations. So first one comes from dou E by dou A equal to 0. Second one comes from differentiating the error with respect to B and setting that resulting expression equal to 0. And similarly dou E by dou C, and then setting that resulting expression equal to 0. So these equations 1, 2 and 3, so these are called normal equations. So these are called normal equations. and then we can solve them simultaneously in order to get A, B and C, so that the corresponding error will be minimum, because equation 1, 2 and 3 states that the change in error with respect to A is equal to 0, the change in error with respect to B is equal to 0, and the change in error with respect to C, that's equal to 0, and this corresponds to a stationary point, and that point is nothing but the point in a plot of error versus some of these values, your constants. That point will be stationary point where your error will be minimum. And if you want to prove that this point is minimum, we still can calculate dou squared E by dou A square. We can calculate dou squared E by B square, dou B square plus second partial derivative of error with respect to C, and then we can substitute the values of calculated values of A comma B comma C, and we will see that resulting value will be positive, and that means the stationary point which we are talking about E, that will be minimum. Yeah, so that's the principle of least square. So at the moment we solved it for the polynomial expression. So maybe in the next video I will solve a simple linear expression, say something like that looks like y is equal to mx plus c. So what this equation states is you have some x value which is your independent variable, you have some y which is a dependent variable, and they are represented by an equation that looks like this. So which is y is a function of x, which is equal to mx plus c. So if you want to find m and c where your error will be minimum, for which the error will be minimum, so to meet that condition, again you have to find how the error change with respect to m and how the error change with respect to c, and this should be equal to minimum if you have to find the, so this should be equal to 0 in order to find the stationary point where your error will be minimum. Say you plotted here m and then you plotted here error. So this point, this is the point where error will be minimum, and this, to get that point you have to differentiate dou e with respect to dou m and set this equal to 0. So this is the stationary point where your e value will be minimum. And similarly, if you plot c versus error, again you have to find a stationary point where your error will be minimum, and this should be equal to change in error with respect to c. This should be equal to 0. So this is something I can continue in the next video.